Hello, everyone. Let me pause the music first. Okay, so hello, everyone. Today we got a bit minutes late. No worries about that. So today we have Mehul with us, who is going to talk about introduction to deep learning. And yes, it's going to be a very interesting session because from the past few weeks we have been doing just native machine learning like. Linear regression and all those native machine learning stuff. Today we are going to jump into deep learning, and yeah, I would like to call Mehul on stage. Hello, Mehul.
Hello, am I audible?
Yeah, you're audible. And yes, now I would like to hand over the session to you, and you are uh, good to go. Best of luck.
Okay, so let's begin. Good evening, everyone. My name is Mehul Pardeshi, and today we'll be talking about an interesting subject in the field of artificial intelligence, that is deep learning. A little about myself. I'm a third year engineering student from PVG College of Engineering, Nashik. I'm also a hackathon winner where we won the Winjit hackathon this year. It was where we developed a sentient analysis tool using the concepts of deep learning and machine learning. And last but not the least, I am today's speaker, and I'm also a team member in ML Nasik. Okay, enough about me. Let's get into deep learning. Okay, what we will be learning. So, first of all, I would like to make clear that we'll be creating a fully connected neural network architecture, like how to create neural networks, how do they work, how do they learn, how we can apply these neural network architectures, these neural networks to ML problems, which are basically of two types, regression and classification. Thirdly, we will know what is SDG, or also called as stochastic gradient descent. And last but not the least, we'll know how to improve the performance of our neural network, like the neural network which we'll create, like how we can improve the performance, how we can make it more accurate, how we can make it more precise, and how we apply those techniques like dropout, batch normalizations, and some other techniques. Now at first, when you heard all these names like regression, classification, stochastic gradient descent, dropout, batch normalization. These seems like, they're very heavy words for people who are just getting into deep learning. But believe me, we are going to cover all these topics today, and they are easy to understand if you pay attention to it. Okay, so as you can see, we have artificial intelligence, which is a general term. Under that umbrella, there is machine learning, which you may have, covered in all these previous sessions in our ML study jam. And lastly, we are into deep learning, which we are going to learn today. So the only thing in deep learning is, on a basic level, it's a subset of ML, machine learning, in which we make multi-layered neural networks from vast amounts of data. So the data here which we use, like it's a lot. Hence the reason the outputs of DL are mostly more accurate than ML. Okay, before starting into what deep learning is and the techniques which we just mentioned before, I would like to, just have a brief introduction of what is the difference between machine learning and deep learning, because oftentimes, people they get confused between ML and DL. Okay, so the first things first. In ML, we require a structured data, okay? We have to, we use pandas libraries and some other libraries from Python where, we format the data. We have a structured data where we use in machine learning. While in deep learning, we do not require structured data. Secondly, when we are making machine learning algorithms, projects that involve machine learning techniques, it requires some sort of human intervention. And as you know, wherever there is, human intervention, they are bound to make mistakes. As humans, we are bound to make mistakes. So in ML, Yes, there can be mistakes. The chances of mistakes are more. While in deep learning, there is no human intervention, right? The use of human intervention is very less, or they, even if they don't exist, okay? So when we don't have human intervention, there is no mistakes. So deep learning techniques, deep learning architectures are less prone to mistakes. Third, okay, now this is very important. When we make ML algorithms, when we work on ML projects, they can function on our computer CPU, central processing unit. But deep learning requires, heavy computing. It requires more power. And that's the reason we use GPUs. And, that is the reason, deep learning is slightly more expensive because GPUs are more expensive than CPUs. And machine learning algorithms, machine learning projects, they can take seconds, they can take hours. They don't take that much time for, computing process in terms of computing. While when we make neural networks, while we are, working on a DL project, it may take weeks. It takes that much amount of time because in the end, you know, there's a huge amount of data and there is no human intervention. So the machine has to learn by itself and has to do a lot of computing power. So yeah, it takes weeks for a deep learning algorithm or project. Lastly, what's the difference, where we use machine learning and where we use deep learning? So for machine learning, you may have heard, right? Forecasting, weather forecasting, predicting simple applications. Many people who have, listened the previous ML sessions or who have just gotten into machine learning, you may have all made projects, simple projects like, house pricings and, detection projects. So these are some basic projects, basic uses of machine learning. But for deep learning, it's slightly more complicated than that. You have to make, for example, as it's written here, like in autonomous vehicles, or you may say a deep learning technique, for LLMs, for generative AI, and for more complex things, we require deep learning. So as the complexity increases, we subtly shift from machine learning to deep learning techniques. Yeah, so there's one thing I have put here is like what languages do we use in ML and DL? So it's Python and it requires maths, okay? Machine learning itself requires maths and deep learning requires more maths. So maths and Python code it's holding it together, both machine learning and deep learning. And it's always good to explore the depths, and that's the reason why we are here today. Okay. So now, I know this is the introduction about deep learning, but there are many techniques, there are many use cases where we prefer machine learning over deep learning, and there are reasons for it. Firstly, there is less data requirement. As I mentioned before, you use deep learning, there is a huge data requirement. But for ML, you don't need to require that much amount of data. Secondly, there's faster training time for ML algorithms. It just takes seconds or hours. It doesn't take weeks like deep learning. Thirdly, ML, it requires less computational power. So I want you all, just to fix this in your mind. That's the reason I'm again and again going over this. So next time when someone asks you, okay, then what's the difference between ML and deep learning? So you should know, okay, there are less data requirement. It is a faster training time. ML requires less computation power. In ML, there's a less complex models. The complexity is very less in machine learning. In machine learning, there are simple models, and there's more flexibility as of now in machine learning than in deep learning. The problems, which can be uniquely solvable by ML is, for example, structured data analysis, basic data analysis, spam detection, spam, not spam, market-based analysis, churn prediction, and credit scoring. So as you have gone through all the previous session by ML, you may have all known what is this. You know what are the use cases of ML, what are the advantages of ML. Okay, now we get into deep learning. Just look at this diagram and yeah. So what is deep learning? Deep learning is a subset of machine learning that uses artificial neural networks, which is inspired by human brain. We all know, we have all learned in our class ninth and class 10th about neurons, right? So deep learning architecture, the base architecture is based on that. It is inspired from that. It uses artificial neural networks. So, okay, one thing I would like to mention is all of you, just pay attention to the bold words written here, which I've written here. They are like the keywords. Okay. So it's a way to teach computers to learn from data, similar to how humans learn from experience, right? So in our day-to-day life, when we wake up, we do things. This all data, this all information is getting gathered by our neurons, getting transmitted by our neurons in our brain, and we learn from that, right? That same model has been applied to deep learning or to neural networks. Neural networks work in a similar fashion. They learn from the data. Deep learning uses layers of interconnected neurons to process the information. Like in human brain, you can see the neurons are connected to each other. Exactly in the same way in deep learning, our neurons, right? Neural networks, they are connected to one another. The reason I'm again and again giving an example of a human brain is because it is inspired from that, right? So it will be more easy for all of us to connect deep learning and our human brain, neurons and neural networks. Yes, each neuron individually performs only a simple computation. Now, I just told you at the beginning to pay attention to the diagram here, right? This thing is a simple neural network, a simple neuron, as you may say, artificial neuron. So this one thing does only one simple computation, right? So we create neural networks, right? So there are layers. So these layers, they form a network that can recognize patterns and make decisions. You can see, face recognition, some sorts like that, right? It recognizes patterns and it can make decisions on its own. Hence the reason we don't need human intervention here. So as the network processes more data, it improves its accuracy over time. Exactly how our human brains work. The more data we get, the more information we process, the more accurate we become over time. Same, our neural networks, they work in a similar fashion. The more data you feed them, the more accurate they become. Deep learning is okay. In our previous slide, right? I just told you, we just talked about why, what are the advantages of ML over DL and what are the problems that are uniquely solvable by machine learning. So, what are the problems that are solvable by deep learning? So, deep learning is, very good at tasks like image recognition, speech understanding, language translation, and it is embedded into our day-to-day life. Like if you can open your phone and there's image recognition, there's speech understanding, text to text, there's language translation, Google Translate. These are all based on deep learning techniques. So why is it called deep? Right? I'll ask this question later also in the slides. So it is called deep because it uses layers of neurons. There isn't a one layer of neuron, there are layers of neurons to handle complex problems. Okay. Which of the following problems are uniquely solvable by deep learning? We just talked about machine learning, deep learning. What is machine learning? What is deep learning? So, can anyone tell me in the chat box which of those following problems are uniquely solvable by deep learning? I'll just give you a minute. Just, remember what all things we just discussed. There are, things that can only be solved by machine learning. There are things that can be only solved by deep learning. So let's go through the first one. Identifying and categorizing objects and images. Well, this seems like it is solvable by deep learning. So yeah, this thing, it can be solved by deep learning. Second, predicting customer churn in subscription-based services. I think so this is solved by machine learning. Third, converting spoken language to text. Again, this is very easy. Image text translation. It's deep learning. Fourth, detecting spam emails. It's machine learning because As we mentioned before, detection of spam emails is a problem that is solved by machine learning. Fifth, translating text from one language to another. Again, it's deep learning. Translation, deep learning. Sixth, assessing creditworthiness using classification algorithms. Well, this is machine learning. So there's 1, 3, and 5. These are the correct answers. Okay, did you notice this image right here, right? I said you like this is a simple neuron. Now it has a name. It's called as a perceptron in deep learning language, okay? This is called as a perceptron. Now you may see there are some variables written here. X, 1, W, V, this plus sign and this Y. So what are these? So the input is called as X. So this is the input here. So it has a connection to the neuron and it has some weight. So W is the weight. Okay, now you may ask what is B? So B is a special kind of weight which we call bias. Okay, so the bias doesn't have any input data associated with it. Hence the reason it's 1 here because anything multiplied to 1 is the value itself. So why do we use this bias? So the bias enables the neurons to modify the output independently of its inputs. So by using bias, we can, modify the output independently without changing the inputs, without changing the X and the W. A neural network learns by modifying its weights. Yes, like as you mentioned before. So, like you may ask, okay, so what is the activation function of it? So how do we activate this particular perceptron here? So what is the formula is Y is equals to W into X, means weight into the input, right? Plus B into 1. So B into 1 is B. So we get the formula as Y is equals to WX plus B. Have you seen this formula somewhere in your 9th standard, 10th standard, 11th or 12th, or even in engineering, we have this formula during our first year, I guess. Yeah, that's exactly right. This is the equation of a line. I mentioned you before, right? There is maths present here. Without maths, there is no deep learning, there is no machine learning. So there will be math concepts used here. So yeah, you should have a good understanding of maths. So yeah, this is the equation of a line. Y is equals to Wx plus B. It is called the slope-intercept equation, where W is the slope and B is the y-intercept. So let's take an example, okay? Like how does this perceptron work? So as input, we'll take a sugar, okay? We'll take sugars as input. We'll have some weight attached to it. So here the W is 2.5 and the bias we'll take as 90. We can take bias as per your data set, as per the question. Here we are taking as 90. And we have to predict what is our output calories. So we have to take sugars as input and we have to predict how many calories, that particular sugar will give us. So, okay, we'll take input sugar as the value of input sugar as 5. So now let's use the slope intercept equation. So if we use the formula as y is equals to wx plus b, we'll get 5 into 2.5 plus 90 into 1. So that amounts to 102.5. So what does it mean? It means that 5 grams of sugar per serving will have 102.5 calories, right? This is how an example, how we use perceptrons to take an input, how we process it, and how we get the output. Now just tell me, what if we wanted to expand our model to include things like fiber and protein? Here we're taking only as sugars, right? And we're predicting the calories. So what if we take input like fibers and protein content also along with sugars? It's simple, right? We'll just expand our input. So yeah, we'll take as x naught as sugars, we'll take x1 as fiber, we'll take x2 as protein content, and yeah, we'll take bias. We have to take bias. Bias, every time we do something, the bias is attached to our perceptron, to our neural network. So we just add more input connections to the neuron, one for each additional feature. Okay. So there's one important term here called feature. So we'll call our inputs as features from now on. Okay, now we'll just find the output. We'll use the same formula. Y is equals to Wx plus B, right? We'll just expand the formula now. Y is equals to W naught into X naught plus W1 into X1 plus W2 into X2 plus B into 1. So we get the formula. For this particular neuron, this is the formula. This is our activation function. So the easiest way to create a model in Keras is through keras.sequential, which creates a neural network as a stack of layers. So I have pasted a small code snippet here. So where we import, okay, so TensorFlow, as you may have all learned and come across in these previous sessions of ML Study Jam. So you may have all known what is TensorFlow, what is Keras. Yeah, okay. So we'll import TensorFlow and we'll create a model where we'll use this thing called keras.sequential because we're creating a sequential neural network. We'll write tf.keras.layers.dense, and as you may see here, it's written 1 comma input shape is equals to 3. So can you tell me why we have written 1 and why we have written as input shape as 3 for this neural network, this perceptron here? So the reason we have written 1 is because we have one output, and the reason we have written 3 is because we have three features, we have three inputs. So why is the input shape a Python list, right? As you can see here, a tuple or list, we can write anything. It's because as we solve more complex problems like image recognition, text-to-text translations, we may have, complex inputs which may require two-dimensional or three-dimensionals also. We may require a huge list. So that's the reason we use list and tuple while creating our input shape. So we'll do one thing. I have here, I'm using Google Colab here, and this is just an example I'll just show you, which I've already done. So here we have the Redwine CSV file. We have used pandas data frame. And yeah, we want to take all these columns as our inputs, as our features, and we have to predict the quality. So we'll take, so as you can see here, we used redwine.shape. We have used dot shape function, and we have got 1599 rows and 12 columns. So we'll take input shape as 11. The reason we're taking input shape as 11 is because we only have to take 11 columns, and the 12th column we have to predict. So that's why instead of taking all the 12 columns, we take only 11 columns and we'll predict the last column. See, then I've used same what we have learned just now, import TensorFlow, and we'll use keras.sequential to create our first layer. So we'll have one input here, and we'll have one output here, and we'll have 11 inputs. So hence the reason input shape is equals to 11. Okay, coming back to our slides. Now we know how to create a layer, a neural layer. Okay, what is one, why we write three, where to write. So we have understood that now. So, okay, time for another question. What does the bias term B in the perceptron do? Can anyone tell me? Option A is it adjusts the slope of the line. B is it modifies the output independently of the inputs. C is it increases the number of input connections. And D, it changes the weight of each input. Well, it doesn't adjust the slope of the line. It doesn't increase the number of input connections. Bias doesn't do that. It definitely doesn't change the weight of each input. We don't want to change the weights of every or of our input. So B is the correct answer. It modifies the output independently of the inputs. Hence the reason, that is the reason our neural networks learn. So bias plays a very important role actually in learning of our neural network. So it modifies the output independently of the inputs. Coming back to layers and activation function, right? You may have heard me, I'm using this sentence, activation function when I was saying y is equals to wx plus b, activation function. So what is activation functions and what are layers? For till now we are just visualizing. Now we'll just see like what are those. So an activation function is simply some function we apply to each of the layers outputs, its activations, and the most common is the rectifier function. Okay, now see, we are just learning the types of activation functions. There are numerous types of activation functions, and rectifier function, or we call it as ReLU, is one of them. So, and activation functions we apply to each of the nodes, each of the layers outputs. Okay, dense layers by themselves can never move us out of the world of lines and planes. What we need is something non-linear. Without activation functions, neural networks can only learn linear relationships. In order to fit curves, we'll need to use of activation functions. Okay, now this is a huge paragraph. I'll just explain you in simpler terms. The reason we use activation function is to bend the data. Okay, so without activation functions, neural networks can only learn a linear relationship like a straight line. But when we use activation function, it can learn non-linear relationships. Like here, as you can see, fitting a non-linear relationship from the graph, how our model is learning non-linear relationships. And this happens because we use activation function. When we collect together linear units, we have something called a set of inputs where we get a dense layer. So as you can see here, x0, x1 are two of the features, two of the inputs. There's one additional layer, and then there's an output layer. So there's additional in between layers of input and output. All the layers which you're going to use, they are collectively called as dense layers. Here we can see the rectifier function, the graph of the rectifier function. Let's look more into it. Okay, as I have told you mentioned before, hidden layers. So these are also called as dense layers or hidden layers, whatever you may prefer, you may call it hidden layers or dense layers. So let's start. The layers before the output layer are sometimes called as hidden because you never see their outputs directly, right? So the thing is, suppose you give an input, right? You give an input of x0, you give an input of x1. The outputs will get processed. It will be processed by our hidden layers, by each individual neural net neurons present here, perceptron present, and it will go to the next hidden layer. And then it will process something and it will go to the next hidden layer. And sometimes it will go to the output at the end. So in this entire process, right, you will never see the output of the hidden layers or the in-between layers. You will just directly see the output. And hence the reason they are called as hidden layers because they are hidden from us. Now, can you see on the hidden layers, you can see this a line, right? A V type of line. You know what is that? That is rectifier function. Our activation function is there. So that means our activation function has been applied to on that layer. Okay. So whenever you see a neural network or a diagram or a flow chart, and you see this sign, it means ReLU activation function is used there. Then why hasn't that sign, why we haven't applied this activation function on our output, our final layer? It is because we don't apply ReLU activation function on our final layer. We use there's one more activation function called as softmax. Yeah, that we use on our output layer, but not ReLU. Remember this. So the rectifier function has a graph that's aligned with the negative part rectified to zero. Applying the function to the outputs of a neuron will put a bend in data, moving us away from the simple lines. Again, I'm just repeating myself, is to pay attention to the bold words which I've written here. Bend in data, negative part rectified to zero. As you may see here, where I told you to look at the rectifier function graph. You may note if you see properly, right, all the negative values, they are rectified to zero. And as soon as the positive value starts, there is a value there. It holds a value. So that's what rectifier function is. So when we apply this function, it bends the data. That means our data can fit non-linear relationships. When we attach the rectifier to a linear unit, we get a rectifier linear unit or ReLU, right? We're just telling that. The sequential model we have been using will connect together a list of layers in order to first to last. The first layer will get the input and the last layer will produce the output. I've attached the code snippet here. Let's look at it. Okay, so here we have used concrete CSV. As you can see, this is a data frame of concrete CSV. We have input shape as 8, so we have 8 features here. Okay, now just look at this cell. Okay, we imported TensorFlow. Here we are creating layers. So here we are creating hidden layers or dense layers. tf.keras.layers.dense. This is the first layer. Okay, 512 activation is equals to ReLU and input shape is equals to input shape. So input shape is 8. 502, the 502 means there are 502 neurons. Okay, and on that neurons, on that 502 neurons, we have used an activation function. And what activation function we have used? We have used as ReLU. We have used ReLU activation function. So as you can see, there are 3 layers here, each layer containing 512 neurons, and every layer has activation function ReLU on that. And then we have one output layer. So this is how you create layers in neural network in deep learning. And this is how you can use activation functions. You can apply activation functions to those layers. Okay, so now you all know. Now we all know how to create layers in deep learning, how to create layers and how to implement, how to use activation functions. What is activation function? What is ReLU activation function? Why do we use activation functions in neural network? A, to learn linear relationships between inputs. B, to move from simple lines and planes to more complex relationships. C, to increase the number of layers in your network. Or D, to connect layers in sequential model. It's B. We to move from simple lines and planes to more complex relationships. That's the reason we use activation functions. Okay, how to train a neural network? Training the network means adjusting the weights in such a way that it can transform the features into target. So we use two things here, the loss function and the optimizer, the stochastic gradient descent. So let's look at the loss function. A loss function is that measures how good the network's predictions are. A common loss function for regression problems is the mean absolute error, or in short form, MAE. So what is the math behind mean absolute error is the absolute of y true minus y pred. So okay, what is y true? What is y pred? Y true means the true values of our data set or the column we are predicting of our target, and y pred is the predicted values from the neural network. So when we minus the true value minus the predicted value and we take the absolute of it, we get the loss. So and we can plot that loss. So from loss function, right, from using this mean absolute error, we can just check what is the loss of our neural network, and we can just predict how good the network's predictions are. So there's also there's another loss function called as mean squared error or MSE, and that has its own formula to it. So there are many laws, there are few of the loss functions which you use, and this is for regression problems. Secondly, the optimizer or stochastic gradient descent. So now we understood what is loss function. Now let's see what is optimizer. Optimizer is an algorithm that adjusts the weight to minimize the loss. Okay, so this is very interesting. Okay, loss function, it measures the loss and it tells us how good the network predictions are. And what optimizer does is that it adjusts the weight to minimize the loss. So like they're working together. Okay, and when they work together, we get a more accurate neural network. There are two more important terms here which we need to know is something called as batch and epoch. So what is batch and what is epoch? You may come across this in machine learning and in deep learning. So each iteration sample of training data is called as batch. and while a complete round of training data is called as an epoch. So these are the textbook definitions. So there are multiple iterations. So whenever there's an iteration, it's called as a batch. And when you iterate through the entire data set, then it's called as a one epoch. Base simple. Okay. As you can see, there's a GIF here. So when we use loss function and the optimizer in combination in our neural network, our neural network, it makes our predictions more accurate. And you can see how the line is tilting towards our data. So it's getting more accurate. The training loss, it's going down as the batch increases. So that's good. Our training loss is getting going down. And our batches, they're going up to the weights. So this is good. So this means our neural network is learning perfectly fine. And the reason it is doing that is because we are using loss function and optimizer function. And there are too many choices, there are too many options. It just depends on how you use them, when you use them, or on what problem you're working on. Okay, back propagation method. So this is a heavy word which, many people who are into deep learning, they may say, okay, oh, let's use back propagation, or you may have come across this term, back propagation. So now just understand it in a very simple terms, on a very basic level. What is back propagation? So what is it? It's a method used to train neural networks by adjusting the weights of the network. Okay, just so what it is, it just adjusts the weights of the networks, and it is used for training. So how backpropagation works in simple terms? Forward pass. Data is passed to the neural network from input to output, and the predictions are made. Right? We get the data from input, and it is passed to the next layer. It is passed to the next layer, and then finally it is passed to an output. That's the forward pass. Loss calculation. The difference between the predicted output and the actual target is calculated using the loss function. As you have seen before, as I explained to you before, what our loss function does, it is for it is the absolute of true values minus the predicted values. So there's a loss calculation there. Okay, so now that what is called as back propagation or backward pass. The loss is propagated back through the network layer by layer, and the algorithm calculates the gradient or partial derivative of the loss with respect to each weight in the network. So what this means, what does backpropagation mean is, as the loss is calculated for every layer or every neuron, so now what that does is the loss is propagated back through the layer. So it traverses back again, layer by layer. And our algorithm, right, it calculates the gradient. It calculates the gradient of the loss with respect to each of the weight of the neural network. So as I said you before, right, every neural network, it has a weight attached to it, right? So it maps that with respect to that weight, and backpropagation is achieved. So when it calculates that, it just checks, what is the difference. So using the gradients, the weights are adjusted to minimize the loss, usually with an optimizing algorithm such as gradient descent. So in the end, backpropagation is just a method to train our neural networks to reduce the loss and to make it more accurate. Now, if you go deep into back propagation mechanism, you'll find, huge formulas that are used, huge algorithmic formulas that are used behind the scenes. Will not discuss that here because, we are just keeping it basic, and I'm just giving you a basic idea what back propagation is and what does it do. Okay. What is the purpose of back propagation in neural network training? A, to calculate the mean absolute error. B, to pass data from input to output. C, to adjust weights while calculating gradients to minimize loss. And D, to optimize the loss function directly. Now, many of you will find this, oh, the answer may be D, or the answer may be A, or the answer may be C. It may be confusing at first, but the answer is C actually. To adjust the weights by calculating the gradients to minimize the loss. That is the purpose of back propagation in neural networks. Okay, so now let's see what is learning rate and batch size. I just mentioned, I think so in my first slide, we'll be learning about these things. So yeah. So what's learning rate and batch size? I have the same GIF here. So the size of the shifts, right? As you can see our line, it is getting shifted to our data points. So the size of the shifts is determined by something called as learning rate. Their interaction is often subtle, and the right choice for this parameter isn't always obvious. So the thing is, when you create a neural network in deep learning, you may have it isn't predefined. You have to write this should be the learning rate or this should be the batch size. You have to experiment with it a little. You have to sometimes increase the batch size. You have to sometimes decrease the batch size. You have to sometimes increase and decrease the learning rates. You have to play around with it a little and till you get the perfect values of both learning rate and batch size. And yes, it is different for every problem you solve or every data set you have. So a common SDG algorithm is called as ADAM. So ADAM is an SDG algorithm that has adaptive learning rate that makes it suitable for most of the problems without any parameter tuning. I mentioned just now, right? You have to play with the learning rate. It is not always obvious key. It has to have that fixed value. So we use something called as ADAM. So ADAM is called as adaptive learning rate. So it automatically adjusts our learning rate according to the problem we're encountering. Overfitting and underfitting. I think so many of you have already learned what overfitting and underfitting is. I'll just give you a basic idea, just a recap or refresh. So signals refers to the actual patterns and relationships in the data that are useful for making accurate predictions. So we use something called as signals. Signals is okay. I'll just read this and then I'll give you a very good example of how I understand our overfitting and underfitting. Noise refers to random errors or irrelevant information in the data that do not contribute to the underlying patterns but can still be fitted by the model. So now just notice on the bold words here. Signal are useful. Noise do not contribute. So basically, just imagine a honeycomb, okay? Just imagine a honeycomb. Now you extract honey from that honeycomb. So honey is the signal, is the useful things you want for making the accurate predictions. And the leftovers, which do not contribute in our learning, is the noise. So what is underfitting and what is overfitting? We can from signal and noise, we can understand these both terms. So underfitting the training set is when the loss is not as low as it could be because the model hasn't learned enough signal. So when the model hasn't learned enough, it underfits. And what is overfitting? Overfitting the training set is when the loss is not as low as it could be because the model has learned too much noise. So and overfitting is like when the model has become too much accurate, it gives you 100% accuracy. So yeah, that's also wrong. That's the reason in machine learning and deep learning, if you say, oh, my model is 100% accurate, something is wrong in it and your model is overfitting. You have to find that perfect balance between these two things. Now, there's one more thing, the last paragraph here, which is very important. The training loss will only go down either when the model learns signals or when it learns noise. But the validation loss will only go down when the model learns signal. So always remember, you have two things, right? You have the train test and you have the test set. So when you're making predictions on training data, you'll always get a more accurate response. The accuracy level will be high. But when you test it on the validation data, your training, your accuracy will go down. So that's the thing you have to remember. One more thing, early stopping. What do we mean by early stopping? Look at the graph here, early stopping, and just read the definition. Okay, we'll just read the definition. Early stopping is a technique where training is stopped once the model's performance on validation data stops improving, preventing overfitting. Look at the bold words again. To prevent overfitting, we use a technique called as early stopping. As the name suggests, early stopping. It means it will just stop early before the model overfits. As you can see here, the training loss, it goes down with every epoch. But the validation data always it goes down and after some point it starts increasing again. So when we notice this graph, right, of validation data, when it starts increasing, it you have to just understand it means that our model has started to overfit. So to avoid this, we use something called as early stopping. So early stopping, what does it do? As soon as it notices the pattern that the validation data has started to rise up again, it just stops. It just stops at training. It stops at epoch. So one thing, if there hasn't been at least an improvement of 0.001 in the validation loss over the previous 20 epochs, then stop the training and keep the best model you found. What does this mean? Can you see the code snippet here? Early stopping is callbacks.early stopping. We just import early stoppings. We have the patients as 5. We have set the patient as 5 and min delta is 0.001. And then we have restore best weights as true. So patients is equals to 5. It means 5 epochs and min delta is 0.001. So that means if there hasn't been at least an improvement of 0.001 the validation loss over the 5 epochs, then we have to stop the training and then you have to restore the best weights. So I may have a code here of early stopping. As you can see, early stopping Adam optimizer. Yeah, early stopping. Patience equals to 5, min delta is equals to 001. And yeah, then we create our neural network 128, 64, and 1. We apply the activation functions of ReLU. And you see, as by using early stopping, we can just make our accurations more more accurate, and we can stop our model from overfitting. There's a meme here, right? See, my model about to overfit and early stopping, just stopping our model from, it prevents it overfitting. Just remember one thing, we use early stopping to prevent our model from overfitting. The thing I've written here in highlighted is wider networks have easier time learning. The reason we use wider network means more neurons, 512, something like that, wider networks. The reason we use wider networks is that if you want to learn more linear relationships, it has easier time learning more linear relationships. While deeper networks, like for example, 128, 128, 64, 8, 1. So this is a deep network, right? We have many layers in it. So we use these types of networks when we want to learn more non-linear relationships. So this is just a suggestion here. Like if you whenever you have to make a neural network, if you want to learn about linear relationships, it's better to use wider networks. And when you want to learn about non-linear relationships, it's better to use deeper networks. What is the purpose of early stopping in training the neural network? Option A, to adjust the batch size dynamically. Option B, to increase the learning rate gradually. Option C, to ensure the model is trained for a fixed number of epochs. And D, to prevent overfitting by stopping training when performance stops improving. So yeah, the answer is D. To prevent overfitting, always remember, early stopping equals overfitting. To prevent overfitting, we use early stopping. So to prevent overfitting by stopping training when the performance stops improving, you can just select yourself. Like in the last example, we had 0.001. You can, make changes according to your own preference. So that's the reason we use early stopping to prevent overfitting. Okay. So I think so. This is our last topic, I think so. Dropout and batch normalization. So what is dropout? We'll check what is dropout. Dropout is a technique used in neural networks to prevent overfitting. So okay, this is one more technique which is used to prevent overfitting. So what is the difference between the previous thing we learned and dropout? During training, it randomly drops out or turns off a certain number percentage of neurons in the network, forcing the model to be more robust and not rely too heavily on a single neuron. As you can see here in the GIF here, there are certain neurons that have been dropped off or it has been turned off. So what does this do is that a single neuron, it doesn't learn too much, or the our network, it doesn't rely too much on that single neuron, and it makes our network more robust. So that's a technique called as dropout. So it prevents overfitting, and it makes our neural network more robust, and it doesn't a neural network doesn't rely more heavily on any single neuron. So now what is batch normalization? Batch normalization adjusts the outputs of a layer to have consistent scale, which helps the model train faster and more reliably. So this to understand this visually, I have pasted a diagram here. When we don't use batch normalization, right, our outputs, our inputs, right, or whatever our data set is there, right, there are huge difference and there's too much disturbance in that. For example, it's like, 10, 20, 30, then suppose 500, 2000. So you can see the difference is too much. I'm just giving a very vague example for understanding batch normalization. So batch normalization, it normalizes scale. It makes it more consistent. So when we use batch normalization, right, it will just use a formula behind on the back end and it will normalize our data. It will make it more consistent, more smooth. So when our data gets more smooth, more consistent, what does it do? Our model, it will learn more reliably, it will learn more faster, it will learn more easily. So that's the reason we use batch normalization. The outputs of every layer or specific layers chosen by the user gets normalized, not just the final layer. This helps in making the training process more stable and efficient throughout the entire network. So you can apply batch normalization techniques to every layer you want or specific layers as per the choice of the user. It makes our network more stable and more efficient. It reduces that randomness, it reduces that variance in our data. And that's the reason we use batch normalization. So the one thing we use batch normalization is something called a standard scaler or min-max scaler. So use techniques of standard scaler and min-max scaler to normalize our data. So tell me one thing. As you can see the GIF here, right? Just tell me what percentage dropout has been added here. If you can see, right, there are four neurons here, right? And at any particular given of moment of time, two neurons are getting dropped off and two neurons are on. So that means 50% dropout has been added to this layer. I'll also just show you the code of batch normalization and dropout layers. Okay. Yeah. Okay. So just here, model is equals to keras.sequential. We have three layers here, 512, 512, 512. We have applied activation function relu on it. And see, we have used this layers dot batch normalization. We have batch normalized every layer here. So here we are using batch normalization techniques. We have used optimizer as SDG or stochastic gradient descent, loss as MAE or mean absolute error. And you can see by using batch normalization, our value loss and our predicting loss goes down more properly, more efficiently. The data is more consistent, and our accuracy of our model increases. Okay, so now we know what is dropout and what is batch normalization. Okay, accuracy and cross entropy. This is our last topic for today of deep learning. What is accuracy? As the name suggests, accuracy is a metric used to measure how well a model is performing. It is the ratio of correctly predicted instances to total instances. So the formula of accuracy is number of correct predictions divided by total number of predictions. That's the formula of accuracy. It just tells us how well our model is performing. Okay, now what is cross entropy? Cross entropy is also known as log loss. It is a type of a loss function used in classification problems. Now remember one thing, the loss function which I told you, right? Mean absolute error, mean squared error, they are used to regression problems, and cross entropy, they're used in classification problems. It measures the difference between predicted probabilities and the actual class labels. So a very simple example of cross entropy here is, A classification problem where we use cross entropy is binary classification. Example of binary classification is spam and not spam. So what is binary classification? Binary classification is a type of classification problem where the goal is to predict one of the two possible classes for each input. For example, deciding if the email is spam or not spam. So here, as since this is the classification problem, we'll use cross entropy. And this too has has different types of formulas at the back end, same like back propagation mechanism. So as I mentioned before, cross entropy and mean squared error. Cross entropy, it is best for classification because it handles the probability distributions and penalizes wrong confident predictions. So that's what cross entropy does. It handles the probability distributions, and if the model is confident about a certain prediction, right? And if the prediction is wrong, so what does cross entropy do? It penalizes that heavily, and it penalizes that model heavily. And mean squared error, it is best for regression because it measures the average squared difference between the predicted and actual values. We have already seen the formula of MSE, absolute of y true minus y pred. So yeah, we use cross entropy for classification problems, and we use mean squared error for regression problems. We can also see the graph of cross entropy. So yeah, so now we know what is accuracy, what is cross entropy, what is mean squared error. Remember, this all are loss functions: cross entropy, mean squared error, mean absolute error, and many more things. They all come under one umbrella of loss function, but certain techniques are used for certain types of problems, like cross entropy used for classification problems, and techniques such as mean squared error and mean absolute error and few other techniques, they're used for regression problems. So yeah, that is the end of our session on deep learning. I hope you understood what I told, what you learned today, what you all learned today. Now we could just go back on the first slide and we could just, check if we have covered all the topics. Yeah. So as mentioned, now we know how to create a fully connected neural network architecture. We know how to apply neural networks to two classification ML problems of regression and classification. We know how to train neural networks with stochastic gradient descent. And now terms such as dropout or batch normalization and many other things which at first we found, okay, what are these words? I guess now you're more familiar with these types of words. So yeah, that is the end of our session today. I hope you all liked it.
Hello, Mehul. I'm back, and yeah, it
Hello.
was amazing session. To be honest, I also got to learn some new things today. Yeah. So hey guys, if you have any questions, you can drop it in the chat box, and we will be happy to answer. Mm, Let me see how many of them are watching right now. I see 13 people watching it. Uh,
Okay.
yeah. Okay, I think no one has any questions, and you also finished the session on time. So the slot
Yeah,
that was given to you was 1 hour, and you made it like proper 1 hour.
proper one.
That's really awesome. Um, Seems just like me, you have explained things quite well, and no one has any questions.
That's good.
And Okay, I think then we should end the stream. I'll just get your screen uh, outside. And is there any noise coming from my side? Or it's all fine.
Not that much. It's okay. I can hear you clearly.
Yeah, because there's some noise outside. Okay, I think we can end the stream now. And yeah, let's play some music like yesterday.
Yeah.
And once again, bye bye.
Thank you. Thank you for having me.
Yeah, thanks, Mehul, for the awesome session. See you guys on
See you
next
everyone. Bye
weekend.
bye.
Yeah, bye bye.